we're going to take a look at the derivation of the formula for curvature for a vector valued function r of t here. And we've got to note, of course, that r prime of t is going to be non-zero on this one. And that's because we first want to recall that our unit tangent vector is r prime of t divided by the magnitude of r prime of t. And in order for this to be defined, we have to have that magnitude, of course, is non-zero. And we're using this particularly because we want to note that the unit tangent in a way indicates the direction that a curve is going at a particular point. And we can illustrate that, pretty quickly here. I'll just sketch in a rough graph. We're actually going to use this to help us understand why we define what we do for our curvature here. So we've got, this is our function r of t here that we're going to work with. And again, this unit tangent indicates the direction that we're traveling at some particular point. So at this point, the curve is effectively going this direction. Here it's going like this. Here it's going like that. And all the way around at various points. That's not very tangent. Let's change that and make it look a little better. Again, we're going to use this particularly to help us define what we want for our curvature. That's why I'm drawing all these particular points. I'm trying my best to draw them at regular intervals, because what we want to observe is places where the curvature is very tight. So in here, or places where the curvature is really tight, and then here the curvature is not so much. It's a little flatter curve out there. So what we see is if we investigate how these unit tangents are changing as we go around the curve, we notice that as we get to places where the curve is tighter, the rate of change of the slope of this tangent, if you will, or the direction of it, is really high relative to the length of the curve that we roll through. Again, looking at this particular loop area down here, again, these tangents are changing direction rapidly relative to the length of the curve through here. As we look through places out here, again, if we look over a similar length, we see that the unit tangents don't change quite as rapidly as they do over here. So that is our motivation in terms of how we set up our formula for curvature. Effectively, it's going to measure how quickly the curve changes direction relative to, or with respect to, the arc length. We want our curvature, k of t, to be equal to the magnitude of the rate of change of the unit tangent vector with respect to arc length, s. Now, if we also realize that both these vectors, the arc length and the unit tangent, are really functions of t, then that rate of change can be written as dt d little t divided by ds dt. The numerator here we would just recognize as the derivative of t prime. So this is going to be t prime of t, a quantity that we're familiar with through other calculations that we've made. Now, the denominator here certainly is just s prime of t, but we can actually do a little bit better. So let's make a note. So let's just note that we have the formula for arc length, and that is that it's the integral of the magnitude of r prime of t dt. So now what we're asking for in the denominator, of course, is ds dt, which would be the derivative of the integral. And for all intents and purposes, the integral and the derivative will effectively cancel each other out. There's a lot of mathematics that goes on behind the scenes, but effectively we end up with ds dt being equal to the magnitude of r prime of t. So now we've got a replacement for our denominator, which is the magnitude of r prime of t, and I should have magnitude in the numerator here as well. So this is how we typically remember our formula for arc length. Again, the motivation here is that we wanted the rate of change, how quickly these vectors are changing direction relative to some arc length that we've gone through.